Welcome to the session 9 of Unit 2 in digital signal processing. So in this session, let us try to understand decimation in time fast Fourier transform, that is DIT FFT. So let us understand this DIT FFT step by step. So before that, let us consider a discrete time signal x of n with let's say capital N samples, and let us consider its corresponding 8-point DFT, and I can represent it as a pair as shown on the slide. X of n, its n-point DFT is x of k. Okay, so discrete time signal is represented as small x of n, and its DFT is represented as capital X of k. So let us divide this samples of x of n into the two uh, parts. First is the even samples, and second is the odd samples. So let us consider the even samples. Let us indicate the even samples as f1 of n, and let us indicate the odd sample as f2 of n. So what we are going to do here is we are going to divide the x of n into the two parts, one as f1 of n and another is f2 of n. F1 of n consists of the even samples of x of n, and f2 of n consists of the odd samples of x of n. So let us write it as, so as it is even samples, I can consider it as f1 of n is equal to x of 2n, because I want the even number of samples, and uh, for the odd samples we can consider f2 of n is equal to x of 2n plus 1, because I want odd number of samples. So once I indicate this even part and odd part as f1 of n and f2 of n, now we'll start with the our definition of DFT. This definition of DFT, we know that it is equal to x of k summation n runs from 0 to n minus 1 x of n, and then Friedel factor, that is w subscript capital N superscript small k small n. So let us divide this uh, x of n into even part and odd part. So we'll consider the even instance of n, and for even instance of n, I know that it is equal to x of 2n. So I have written here x of 2n. So n will be replaced with 2n. So again here n will be replaced with 2n. And for odd one, n equal to odd, I have x of 2n plus 1. So I have written here x of 2n plus 1, and n is replaced with twice n plus 1. So in this way, I can write the expression. I can split the definition of DFT into the two parts. One part is for the even, and another part is for the odd samples. So you can see here that we have written here that x of, just take me some another pen. Yeah, I have written here that x of 2n is equal to f1 of n, and x of 2n plus 1 is equal to f2 of n. So I have just replace this x of 2n with f1 of n, and I will just replace this x of 2n plus 1 with f2 of n. If you see this first part, then you can observe here, and if this first part is compared with this definition of DFT, you can see here it is, here there is n, and here there is n by 2, and here there is x of n, and here there is f1 of n. So ultimately this first summation I can write it as f1 of k, and it is the DFT. It is the you can say it as the n.2 point DFT. Okay, so n.2 point DFT, f1 of k is a n.2 point DFT. And similarly, you can again see here, that is summation f2 of n and till this point. So again you can consider here it is my n by 2, and it is my f2 of n. So I can write this as f2 of k, this complete, and it is again a n by 2 point DFT, and that is multiplied with this Friedel factor. So let us write this in the next line. So what you can see here is this. So this becomes f1 of k. So I have written here f1 of k, and this becomes f2 of k. So I have written here as f2 of k. Okay, and whatever I have here is w and k that I have written here. So I got the expression. I got this expression for uh, DFT, that is x of k is equal to f1 of k plus w subscript capital N superscript small k f2 of k. So as it is as f1 of k, you can see here that f1 of k, it is having here n by 2, and f2 of k, it is having here n by 2. So f1 of k and f2 of k both are n by 2 point DFT. So that I should write somewhere that f1 of k and f2 of k are n by 2 point DFT. So if as it is n by 2 point DFT, its k runs from 0 to n by 2 minus 1. K runs from 0 to n by 2 minus 1. So n by 2, if n is equal to 8, n by 2 is 4, and 4 minus 1 is 3. So k runs from 0 to 3 for this f1 of k and f2 of k. So let us put the different values of k. Let's say put k equal to 0. So if you'll compare this, so this is uh, k, and so I have written here x of 0. If we'll compare this f1 of k, so I have written here f1 of 0, this k, and this 8. So I can write here w8 0, and this f2 of k, so I can write here f2 of 0. So similarly, I can write all the values of k. So just like this, k equal to 0. In the similar way, I can write k equal to 1. In the similar way, I can write k equal to 2. And in the similar way, I can write k equal to 3. Now, next step is you can delay with whatever the equation I have here. Whatever this equation I have, this 45.6 equation, I can delay this equation by, let's say, n by 2. And after delaying, let us go further, and then we'll discuss. So let us go towards the next slide. Yeah, so if I'll add the delay in 4.45.6 equation, so it like it, x of k will be replaced by x of k plus n by 2. f1 of k will be replaced by f1 of k plus n by 2. This wnk will be replaced by wnk plus n by 2, and f2 of k will be replaced by f2 of k plus n by 2. But this f1 of k is n by 2 point DFT, so this f1 of k plus n by 2 will be equal to f1 of k. This f2 of k plus f2 of k is a n by 2 point DFT, so this f2 of k plus n by 2 is equal to f2 of k. So similarly, so I can put that in this equation, and what you can write is this. So this is the same, x of k plus n by 2. Now this f1 of k plus n by 2 becomes f1 of k. This w and k plus n by 2 will remain the same, and this f1 of k plus n by 2 will become f2 of k, because f1 of k and f2 of k are the n by 2 point DFT. So you can solve this further, and you can split this. You can split this Twiddle factor. So you can split into two parts. One is wn k, and another is wn n by 2. So if I'll see here wn n by 2, if you solve it, it will become minus 1. So this value is minus 1. So we can put this, and I can get this uh, equation. You can see here. So this f1 of k as it is, this f2 of k as it is, and this wn n by 2 is minus 1. So I have written here minus sign, and this wn k will be here as it is. So again, f1 of k and f2 of k are the n by 2 point DFT. So again, I have to run the k from 0 to 3. So just put k equal to 0. So if you put here k equal to 0, you can see here k equal to 0. So 0 plus 8 by 2, that is 0 plus 4. So it would be 4. f1 of k equal to 0. w and k, so it is w at 0, f2 of k, so it is equal to f2 of 0. So like this, just as I have find out this x of k plus n by 2 for k equal to 0, I can do it for k equal to 1, I can do it for k equal to 2, I can do it for k equal to 3. Okay. So once I got this, now let us, once I got these equations, equation from the previous slide and equation from this slide, that is, in the previous slide we got x of 0, x of 1, x of 2, x of 3, and here I got x of 4, x of 5, x of 6, x of 7, and it is in terms of f1 of k and f2 of k. So let us consider that expressions. Okay, so let's consider the two expressions. One is this 45.6, which we have seen in the previous slide, and next is this 46.2. So we just where the whatever which we are seeing here right now. Okay, so let us write that from that expression. Let us try to draw the butterfly diagram. So let us go into the next slide and let us try to draw it. So let us delete all the annotations. So for our ready reference, let write the expressions as what we have considered is x of k is equal to, in the previous slide, is f1 of k, w and k, f2 of k, and the second one is for x of k plus n by 2. Just write it here. K plus n by 2 is equal to f1 of k minus w and k f2 of k. So these are the expressions which we have seen in the previous slide. So let us draw it one by one. So first, let's say x of 0. If I put here k equal to 0, so it will be x of 0 is equal to f1 of 0, w and 0, or w at 0, f2 of 0. So it's just addition. So you can see here, I will consider the adders here, and this what is the thing. So it is f1 of 0 plus w at 0, f2 of 0. Similarly, if I put k equal to 0, sorry, k equal to 1, so I'll get x of 1 is equal to f1 of 1, w at 1, f2 of 1. So for that purpose, I have to consider here w at 1, and then I have to add this f1 of 1 plus w at 1, x of w at 1, f2 of 1. Okay. So similarly, I can do for the other two values also, k equal to 2, k equal to 3. So it is for this one. And if I'll go further for this second one, means x of 4, x of 5, x of 6, x of 7. This equation is for x of 0 to x of 3. This equation is for x of 4 to x of 7. So in that, what you have to do, I have to, what is the change? The change is the minus sign. So I have to consider minus 1. So I will just check here. So this is what is minus 1 here, and I will add it. So you can see here f1 of 0. So this is f1 of 0 minus f1 of 0 minus, so this is minus 1, w at 0, f2 of 0. So like this, I can do the same thing for all other values of k. So this for k equal to 0, k equal to 1, k equal to 3, and k equal to 2, and k equal to 3. So like this, I will get the butterfly diagram in this way. So this is the first step of butterfly diagram. You can see here you are going to find out x of k from f1 of k and f2 of k, and f1 of k and f2 of k are what? Are the 2 point, sorry, n by 2 point DFT, that is 4 point DFTs. And f1 of k is the DFT of f1 of n. And what is f1 of n? f1 of n is the x of 2, and that is x of 0, x of 2, x of 4, x of 6. like this f2 of k is the DFT of f2 of n, and f2 of n is the, or that is x of 2n plus 1. So you can see here it is x of 1, x of 3, x of 5, x of 7. Okay, so let us go further. Now this was the first step. So we have written x of k in terms of f1 of k. Now we will try to divide the f1 of k. Okay, so now we'll we'll divide rather f1 of n and f2 of n into its even and odd samples. Okay, just like we have divided x of n into even and odd samples as f1 of n and f2 of n. Now f1 of n and f2 of n again we will divide into the even parts and the odd parts. So let us consider that u11 of n is the even samples of f of n, and u12 of n are the odd samples of this u12 of n consists of odd samples of f1 of n. Similarly, you can see here that u21 of n are the even samples of f2 of n, u22 of n are the odd samples of f2 of n. Okay, so let us do it only for f1 of n, and then we can do the same thing for f2 of n. Okay, so let us write here that similar to this previous slides, that is 45.6 and 46.2. We can write the same thing for this f1 of k. We can write this f1 of k in terms of u1 of k, u11 of k and u12 of k, and I can write f1 of k plus n by 4 into u11 of k and u12 of k. So similar to the previous things. Okay, so just like you can see here, I will just write it one more time. Let me use the pen. So what we have did the previous, what, just give me 1 second. So x of k we have written as f1 of k, w and k, f2 of k, and x of k plus n by 2 is equal to f1 of k minus w and k, f2 of k. So here we have divided x of n into two parts, that is f1 of k and f2 of k. Here you are dividing f1 of n into u11 of k and u12 of k. Here x of k was 8.dft, so it was 8. Now here f1 of k is 4.dft, so we are writing here 4. Similar to this, if I'll go for this shifted or delayed version of x of k, so you can see here we are just adding here negative sign and here n equal to 8. Okay, so same thing is here happening. f1 of k, it would be u11 of k, and this should be u12 of k with the negative sign, and it as f1 of k is a 4.dft, or you can say n by 2.dft. We have to write here 4. Okay, so from this equation only we can derive this equation. Similarly, just as I have written the expressions for f1 of k and f1 of k plus n by 4, I can write the same expression for f2 of k also and f2 of k plus n by 2 also. Okay, so let us go further now. Okay, so this will keep it as exercise. We can replicate it as in the case of f1 of k and f1 of k plus n by 4. So this should be n by 4. Okay, so let us go further now. So I have got these two equations, 48.3 and 48.4. Now, as we know that f1 of k is a 4.dft, so u11 of k and u11 of k and u12 of k are the 2.dfts. So that just we have written here. Let us go further. So here we have written f1 of k in terms of u1 of k and u12 of k. So this is my u1 of k and this is my f1 of k. Now I have to find the relation. Yeah, now I have to use adders and multiplication to solve this. or to implement these expressions in terms of in between f1 of k and u11 of k. So yeah, so you can see here u11 of k plus w4k u12 of k. So if you put the values here like as u11 of k and u12 of k are the two point DFTs, so I have to use here k equal to 0 and k equal to 1 only. So if I use here k equal to 0, so what we'll get is f1 of 0 equal to u11 of 0 plus w4k u12 of 0. Okay, so u11 of 0 is here and u12 of 0 is here, and I have to add it and multiply it with this w4k. So let us go further and let us understand this. So I have shown here adders. Now you can see here, yeah, so it is u11 of 0 first. This u11 of 0 will come here as it is. Then this w4 0, so it is w40, and this is u12 of k, so it is u12 of k, that is here k is equal to 0, so it is u12 of 0. So multiplication of these two will be added with this u11 of 0, and I will get f1 of 0. Similarly, if I want f1 of 1, so I have to put k equal to 1 here, so it is f1 of 1 is equal to u11 of k, that is u11 of 1, so this is my u11 of 1, then plus w41 into u12 of 1. So just, yeah, so you can see here. So it is w41 into u12 of 1, which is added with u12 of 1. So I will get here f1 of 1. So if I'll go and put here k equal to 0, so I'll get f1 of 2. If I put here k equal to 1, I will get f1 of 3. So let us do it. Yeah, so it is like minus, this minus sign I have to consider. So for that minus sign I have to consider here minus 1, and the same thing will happen. Okay. So this is what is a butterfly diagram for this f1 of k and f1 of k plus n by 4. Similar to this, I can find out just like I would just did it for f1 of k. Similarly, I can do it for f2 of k also, like f2 of 0, f2 of 1, f2 of 2, f2 of 3. Okay, so that I can do. Okay, because it would be odd part, so here it would be x of 1, then it would be x of 5, and x of 3, and it would be x of 7. So that we can do it as a another part. Okay, so let us go further now. Now we know that this, yeah, I have just written the expressions here for f2 of k and f2 of k plus n by 2. So that we can do this similar way, butterfly diagram for the f2 of k and f2 of k plus n by 4. So now what we know is this f2 of, u11 of k are the 2 point DFT, so I can simply find it as per the definition. So you can write the expression as u11 of k is equal to summation u11 of n wkn n by 4. Now n is 8, so 8 by 4, that is 2, so it is 2 point DFT. As it is 2 point DFT, n runs from 0 to 1, so 0 to n by 4 it is 2, 2 minus 1 it is 1. So simply we can put in the values of n here. So if we put here n equal to 0 and n equal to 1, so it would be n equal to 0, so you can see here u11 of k is equal to summation n runs from 0 to 1 u11 of n w2 k n. So it is 2 point DFT. So I can put, once I will put n equal to 0, another I will put n equal to 1. So if you see here, for k equal to 0, I can write this u11 of 0 equal to 0 to 1 u11 of n, and instead of this k I will put 0, so it becomes 0. And you can see here w20 is going to be equal to 1, so its value is 1. So simply I can write here, if n is equal to 0 and n is equal to 1, simply I can write u11 of 0 plus u11 of 1. So it is written as this. So we can get this u11 of 0 equal to u11 of 0 plus u11 of 1. This capital U is the DFT and this small u is the discrete time signal or discrete time sample, you can say. So like this, just I have did for k equal to 0, I can do it for k equal to 1 also. So I can write here u11 of, now you can see this expression, and in this expression you want to put k equal to 1, so you can write here u11 of k summation, then u11 of n, and this w to k n. So now the value of k is 1. So again, we can split this and further, so we can do this, write this n equal to 0 and n equal to 1. So we can write here u11 of 0, w2 0 1, and u11 of 1, w2 1 1. So again, you can see here that it is w2 0, this is going to be equal to 1, and w2 1, this is going to be equal to minus 1, that just I mentioned here. So this minus 1, so it becomes u11 of 0 minus u11 of 1. So that just that is just I have mentioned here. So this is the second point which I got. So like this, uh, yeah, yeah, we have just made one mistake here. It should be u11 of 1. It should be u11 of 1. So this is the expression for u11 of 0, and this is the expression for u11 of 1. Okay. So let us go further now, and let us implement this equation 49.9 and 49.11 as a butterfly diagram. So you can see here u11 of 0 and u11 of 1. So when I want u11 of 0, that is capital u11 of 0, I want it, and I want these two to be added. So I got this addition here, and when I want this u11 of 1, I want it to be, I want u11 of 1 to be subtracted from the u11 of 0. So I have added here minus 1. Okay. So once I got this, now I have to club all these butterfly diagrams. So I know that the first butterfly diagram was like this. So this I know. So I have drawn it. So this was the first butterfly diagram in which I have calculated x of k from f1 of k, and I have drawn this complete butterfly diagram in the previous slides. Now if we'll go further, then what I have to do, I have splitted f1 of n into u11 of n and u12 of n. So I have drawn this butterfly diagram for the relation between f1 of n and u11 of n and u12 of n. Now, and then we have find out this relation for, find out further this part. Just give me 1 second. I find out the this part. So this part, this black one, that is the relation between f1 of n and u11 of k, f1 of k and u11 of k. I can repeat this same here because it is just a replica, and this blue one I can repeat it for 4 times. 1, then here it would be 2, here it would be 3, so that I can repeat because it's a, as it's a this is a this f1 of k is a 4-point DFT, so this it will get repeated here. The another 4 points it will get repeated here, and as this u11 of k is 2-point DFT, it will get repeated here also. It will get repeated here also. It will get repeated here also. So let us finish it. So this is the this black one we have repeated, and then And this is the, just give me 1 second. So this is the uh, duplicated part for the 3 times. So that is what is the decimation in time fast Fourier transform. So you are just dividing the x of n, that is time, means first you are dividing uh, x of n into the even and odd parts. So it would be f1 of nn to of n, and again f1 of n you are going to divide it into the even and odd parts, which is e1 1 of nn, e1 2 of n, and f2 of n is u2 1 of n and u2 2 of n. So you are just dividing the sequence, dividing the discrete time sequence into the even and odd parts. So that is it. That's why it is called as a decimation in time fast Fourier transform. So let's stop here for the session, and in the next session we will try to understand decimation in frequency fast Fourier